show. Yeah, so the world is ending, but we're still going to have class as usual. Because I already learned how to do this shit last winter when I had to broadcast from my basement 5 classes in a row because of snow and cold temperatures. If they shut down Iowa, we're good. We got the Zoom, we got the online portal, nothing's going to change. It's going to be fine. We'll just be in more comfortable clothing. So we've got, let's see here. I'm losing track of the world here. I keep thinking it's spring break already, but not quite. So as I announced over email yesterday, Thursday is open time to finish up homework 3 if you haven't done so already. If you have finished it or you feel good about it, take off early. Have fun. I don't care. I'm ready for a break too. And that way you don't have anything hanging over you before break. This class you can actually take a break from. We have a regular lecture today that I was able to get finished and possibly an example that I highly doubt we'll be able to get to, but I posted it here anyway. So what we are working on right now is homework 3. Let me pull this up. While you guys are getting situated, Kelly, you had sent me an email about switching back and forth in Stata.
Yes.
Yeah, so I just checked this. For NBReg and GLM, when you're running negative binomial models, they do give the same log likelihood. Because I thought I had checked that, and I just rechecked it a minute ago. They do. NBReg is the one that gives you a built-in likelihood ratio test, though.
For some reason, mine was giving me different ones. I'm using a Stata 16, though. I don't know if it makes a difference.
It shouldn't make a difference.
Yeah, it's like only like one.
Only on one, okay. Because the way that... Go ahead.
It was only by one.
By one, okay.
Yeah, so it's very, very, very close, but for some reason, I can run it in 15 and see, but...
Yeah, I don't know why that would make a difference, but on the version I have on my laptop, which I think is 15, I just checked that and they matched. So you should be able to do everything inside GLM for homework 3. If the likelihood ratio test you can compute yourself or use the LR test function between the Poisson model and the negative binomial model. So I did not run into that problem, but it's possible the differences between versions are making it more challenging than it needs to. But otherwise, does anyone have questions on homework 3 as you're working through this?
So for the
section 2.
That's the question 26 to question 29. Are we using the estimate for different sections?
Yes, so these questions 20 through
26 to 29.
Yeah, all of these actually are going to be either an estimate statement or a model parameter. Most of them will be estimate statements because they're all asking for differences, some kind of simple effect conditional on the interacting variables.
I got the 20 before 26 using the plot G and MOD.
GenMod?
Yes.
Why are you switching to GenMod?
For the zero model.
Well, this does not have a zero submodel to it. This is all just one model that's predicting a count.
Okay, so I can use a Glimix.
Yes, staying Glimix. Yep. Yep, there's no zero inflation model in this homework. I don't know. I'd have to look at exactly what you did. You may have gotten lucky.
Okay.
But yeah, just stay in Glimix or Stata GLM, and there's only one model predicting the log count of foods tried. There's no submodel for extra zeros or anything like that. Right. Would it be helpful to review the coding for those, maybe? Yeah, did you have a question? I think I answered her question. She's in GenMod for zero inflation models, but that's not what we're doing here. Okay, what's your question? What's the number? I'm sorry? 18. This? Yes. Ah, yes. So these are slightly different chi-square tests than what I've demonstrated to you before, but they're the same format. So 15 is asking for a joint test of significance for the two main effects in the model that are marginal. So there's two variables that are not part of interaction terms that I wanted you to do a joint test of, and that's 15. 18 is a joint test of all the other variables in the model. So these are either main effects that are conditional on the interaction terms or the interaction terms themselves. So I'm splitting the model predictors into two sets, basically. There's two that are unconditional that have to do with siblings, and then there's the conditional version that has to do with working full-time and food school. Does that help? Not yet? Okay, so should we write out what the model looks like? Would that help? Okay, let's do that. In the coding? Should we just all do it together? Would that be helpful?
Too long for this small.
I know. I figured there'd be questions. I'm totally fine with spending some time answering them. Let's open up coding first, because if you don't have the coding right, the models don't matter, right?
Is this a hurdle model?
This is not a hurdle model.
Or why it feels like it's if?
On the predictor side, it is like a hurdle, because it's if and how much of a predictor, but the outcome is just one set of counts.
So not this.
Mhm.
It's different.
A hurdle is if and how much as an outcome.
Oh,
This is if and how much as a predictor.
that's why I'm confused.
Yeah, it's a similar concept, but on the other side of the equation.
Okay.
So the hardest part of this is going to be coding two predictors for the effects of food school. So NumSchool is the column that exists in your data set currently. So that ranges from 0 to, I think, 5-ish. There'll be some people who have a little more than 5 as possible. So I wanted you to make one predictor that differentiated the children who had not been to food school at all from those who had. I've named that predictor any school, and it needs to look like that. So it's a binary predictor. If you've been to food school, what is the effect of having been at all? Then, amongst the children who went, how many times have you gone? Centered at 1. So it's a regular centered predictor for the cases of NumSchool greater than 1. The tricky part will just be making sure that this one right here stays 0. So when you put it together, when both of these variables are in the model at the same time, the binary one captures the difference between students who never went to food school and those who went one time. The rest of the model then, amongst the people who've went one or more times, the second variable says what is the effect of each additional session. So you got to write the code to make that happen, that pattern. It is like a hurdle model, as we were just discussing, but it's on the predictor side. So you can think of this variable as a qualitative difference, people who are in the program or not in the program. This variable is a quantitative difference for how many sessions they've been in the program. If this variable were not in the model at all, then the interpretation of this one would be different. It would just be those who are in it versus not in it. But because this is also conditional, this one takes on the difference between none and 1. Okay, does that part make sense? Okay, so then if we write out the model. Yeah,
Can you go back to that?
sure.
So my question is, the word number 3,
Mm-hmm.
how attendance to any school becomes 0 in number of sessions, you think?
This one, by taking the number of sessions and subtracting 1, if NumSchool is greater than 0. So the way that I would approach this is probably to say, if NumSchool equals 0, then do. Set that 0, set that 0. Otherwise, If numschool is greater than 0, set this 1 to be numschool minus 1.
Why the minus one?
Because I want it to be centered such that the reference is one session. Mhm. Okay, is that good? All right, now we can write out the model. So I think this one I ended up calling something like num session or something in my example, so that I'll write this out. So we have our model. So we have foods tried. That's my outcome, which is a count. What goes first? Intercept. Is that a 0 or an O? Can't tell. There we go. Plus. Nope. There. Now what? Beta 1 times. What are the predictors in this model? Yep. Whether or not they have a younger sibling. Has young. Whether or not they have an older sibling. Has old. Or those are 0 if they don't. So only children would have 0s for both. What else? Both working. So whether or not their parents both work full time, which 0 is no. Let's go both. I'll just call it. Trying to keep this short in terms of typing. Now what? The two new variables, so we'll call this any school. I'll say any. And number of sessions. Am I done? Interactions among what? Yeah, so the question stated moderation of the effect of, get the exact wording here. Also examine fixed effects for the extent to which the success of food school, both any participation and amount of participation, depends on whether both parents work full-time. So the way I'm wording that makes full-time the moderator. The thing that it's moderating is the effect of food school. But the effect of food school takes 2 parameters. So I got to put that. Move this thing over. So this is going to be a beta 6 times any plus beta 7 times both and any. There. Oh, nope, thank you. This is why Lisa doesn't do things live. How's that? So now that I've got a model, if you got the right -2 log likelihood, you know that you've got the right stuff in your model. If you got the right fixed intercept, then you know what? That everything is centered correctly, because the intercept is the expected value when everything else is 0. So if you have the right -2 log likelihood, you've got the right stuff in your model. The right intercept means your stuff is in there correctly. The parameterization of your fixed effects. That's what I mean by stuff. So now my model tells me how to find anything. So for instance, how do I find, let me move this over. Nope, not that one. Home. There we go. How do I find the effect of, let's say, difference for no versus yes work full time? Both. So if I want to know what the difference is in the number of foods tried for a given child between children of parents who do not both work full-time versus they do, what do I need? So I'm talking about that right there as a starting point. Okay, I need that. The effect of both depends on, at a minimum, beta 3. What else? Which one? Beta 6 and beta 7, right? Now, because both is the thing that I'm trying to get the effect of, I take that out. Factor it out. Here's what's left. So in your estimate statements or your LINCOMs, the effect of both gets a 1. That's the thing you need. At a minimum, you need a beta 3 to contribute to what your effect of both is. Then you would have to fill in what is the value for any sessions. So if it's a child who's not been to food school, this is 0. If it's a child who has been to food school, it's a 1. And then the number of sessions above 1 as this variable. So beta 6 then takes on the difference between 0 versus 1 sessions. Beta 7 picks up after 1 to the additional effect of each additional session.
So if it's a student didn't go to any food school, so beta 6 and beta 7 will share.
If the student has not gone to food school, this part, this drops, and it's just beta 3. So that's what beta 3 means. It's the conditional main effect when all interacting predictors are 0. That means that in the model, beta 3 is the difference in foods tried, log count, foods tried, between parents who don't or do both work full-time, specifically amongst children who do not go to food school.
If student go to about 1, we still need the beta 6
If they go to one session,
or more than 1.
if they go to more than one session, so if they just,
Always have a beta 6
if they go at all, then yes, you always have a beta 6, because that's the, do you go? Yes or no, right? Now, how much do you go? Do you just go one time?
Let's say 2, then we center it
If you say, if I say, what is the effect of both for a student who's been to food school once? What do I type here? 0. If they've been to food school twice, 1. If I've been to food school 3 times, 2. There you go. So the original point of this, back to your question over there, these are the 2 terms that are unconditional. They are not part of interactions. So I was asking about a chi-square test for those 2 terms for the unconditional marginal main effects in the model. Question 18 then is for the fixed effects typo that are conditional main effects or that test moderation. Then that would mean lumping everything else together. They're either conditional main effects or they test moderation. So if I want to know what is the effect of full-time work and food school, I need all 5 of those terms to answer that question. That's what the second chi-square test is asking for. Okay, does that help? Okay, excellent. Other questions I can help with? So I want to remind you there is always a pattern to what I'm asking. So there will be, for instance, $23, the difference in log count per food school session attended if their parents don't work full-time. 24, if they do work full-time. And then 25 is the difference of 23 versus 24. So you'll see this pattern repeat itself. Simple effect for one group, simple effect for the other group, difference in the simple effects. So if you don't know how to figure out the difference, go back to what you already figured out, how to get the simple effect in each group, and subtract. Okay, question?
Yes, so then the widows, then Q32.
Q32.
Different set.
Yes, predicted outcomes.
We're doing the predicted count.
Yep,
So with this one, you have to put all of your things in, right?
yes,
Okay.
yes.
That's where my brain wasn't working.
Yep. Predicted outcome of any kind has every single model parameter in it. Some of them are going to zero out. So I tried to help you. Given no younger or older siblings, that means you can leave these two out for everybody. So we're just focusing on the rest. The other catch, predicted count. Is that what the model gives me? No, what does the model give me? Log count. So to get to regular count, to get to data scale count, what do I got to do to log count? Exponentiate. So there is in SAS, there is an EXP option that you can add to your estimate statements. In Stata, it's either EXP or eForm. Something will work attached to a Lincom. I forget which one, but one of those will work. And if not, get your calculator out. Exponentiate. But that's not what I did in your homework. I figured out how to do it in the software. So yes. All right. Other questions? Nobody? Okay, Zoomers, I'll narrate for you. There's a lot of people looking at their laptops and not answering.
You helped us, and so now I want to do it.
Now you want to do it. Yes, I know. Yes. Thursday. Or our office hours. Yes. All right. I was trying to make it so that Thursday would be the throwaway day since people are leaving early potentially for break, or I wanted to give them the option. But today we got some stuff to talk about. We have a lecture that I actually finished. So that's exciting. Over the weekend. I've got multivariate stuff. So let's talk about this. It's going to have a whole lot of words at the front because I was trying to come up with a framework to explain this, and I had to borrow from several other frameworks I've already developed and sort of mold them together. So this is somewhat of an experiment. But I also realized that you guys come from disciplines where there's a whole nother set of vocabulary used to describe things. So I wanted to make sure that we had a chance to sort of feel this and absorb all the words and make sure that you can apply what I'm trying to describe as a taxonomy to your world. So that's what we got here. There's a lot of words. That's the only part I really thought that we would get through today. So lecture 4, Introduction to Multivariate General Linear Models. So we're out of generalized for right now. We're going to head back after this, but I got to bring just the multivariate aspect first, and then we'll add the link functions and stuff back to it. So this was the big picture of generalized models, right? 3 things that you want to make choices about to fitting your model. We have the link function. So do we need to transform the predicted outcome to something that's unbounded or not? If it's bounded, say, above and below, that's for logits. Bounded only below, that's logs. And there's others too, but those are the ones that are most common. General linear models have a link function known as identity. Remember what that means? Times 1, meaning it's not really a link function at all. But it makes it so that general linear models are a special case of a generalized linear model. Linear predictor. So this is where the predictors go. Do they need main effects? Do they need interaction terms? Do they need nonlinear terms, etc.? This is guided by your design and your hypotheses. So I can't tell you what to put in there. That's up to you. In other classes, I refer to this idea as the model for the means. meaning that these are all the things that predict the conditional mean. If you have an empty model, meaning no predictors, your best guess for any one outcome is just the mean of that outcome, right? Well, if you start from that as a naive reference point, then adding predictors serves to refine that mean. It becomes a conditional mean. It's still a mean in the sense that anybody who has the same values of the predictors has the same expected outcome. It's just that it's customized, it's conditional. So I call that the model for the means in that, what kind of fixed effects do you want? The third part is what kind of conditional distribution. So in general linear model land, it's normal. In models for categorical data, it's Bernoulli or multinomial. In counts, it's some kind of Poisson negative binomial something. The extra piece here that we haven't gotten to this semester where we're turning the page is now how do we need to adapt this set of decisions to address data that have dependency. So that is a term that sounds somewhat negative. Like, it's dependent data, it's broken, we gotta fix it. The word dependency just means correlation. It means you don't have independent outcomes, you have dependent outcomes. Some of your outcomes are more related to each other because of your sampling design. That's what it means. It's not a problem. In many cases, it's the point of making samples that way. But we have to figure out how to interface this idea of dependency into these set of decisions. How do we adjust the model so that we have dependency as part of the model? And that idea of whether those sets of choices, in other classes for multi-level models specifically, I call this the model for the variance. So is it enough just to have a single type of residual or a single stretchy factor where independent observations are assumed? Probably not. How do we change it? And the choices that are available to you are a function of a lot of things. And that is the part that I had some difficulty in trying to come up with a framework for, but we'll see how it goes. So kinds of multivariate dependency. Odds are good the data that you will be analyzing in real life are not independent. Independent samples happen like never, especially if they're from real people, right? Not experiments, but real people in real classes, real hospitals, real students, all that kind of stuff. So dependency arises whenever multiple outcomes are collected from the same sampling unit. So specific cases of that, if you have samples of people, and people are theoretically independent, but you have sampled a single outcome across repeated occasions or under multiple conditions, then the outcomes that come from the same person have dependency. They're related to each other. The term for this, I would say, is called repeated measures data. I use that to refer to repeated occasions with the same outcome or conditions that have the same outcome. So you're thinking of it as one outcome, like say response time. I might want to measure someone's speed of processing, and I might do it in a condition where they have to do something simple and another condition where they have to do something that's more complicated. I'm thinking of it like it's one outcome response time, but it's just under multiple conditions or multiple occasions. That's repeated measures. We're going to start with that one. Multiple persons from the same pair. That's a special case known as dyadic data. So I know Kelly does dyadic data. Shout out to Kelly in the Zoom audience. Does anyone else do dyadic data? Kelly raised her hand. Thank you, Kelly. Yes. Else? So if you collect data from mothers and their children, if you collect data from romantic partners, there's a lot of instances in dyadic data, a boss and an employee, for instance. So in that case, even though you're thinking of them as people still, the unit of sampling that you have to pay attention to is the dyad. So it's the family that has been sampled repeatedly, or the organization, if it's employees and employers that have been sampled repeatedly. Otherwise, if you have people who are grouped because of naturally occurring conditions, that's known as clustered data. So when you sample multiple respondents from the same country, right? Or multiple students from the same classroom, or multiple classrooms from the same school. Anyone else have another kind of clustering? Multiple teachers from the same school? We could do that one. multiple people from the same country, nation, state, etc. In that case, even though you're still thinking of them as people, the multivariate aspect arises because of the higher level unit. So really what you have if you have students nested in schools is that you have a sample of schools, and each school has a repeated measure that is a different student. It's the same idea as having a student who takes a test 3 times if you have a school with 3 students. So the name of it is different, the concept is the same. This problem happens whenever you have more than one level of sampling simultaneously, over conditions and over people and over dyads, over people, over groups. So it's really, really common. How you change the model to build that dependency in, what the choices are available to you, depends on one key feature, whether or not the dependency is balanced or unbalanced. By balanced, that's my word, that other people use that word, but the way that I'm defining it here is to mean that the repeated outcomes are structured in the same way, the same potential outcomes. So if I have a longitudinal design where I have pre-test, midpoint, post-test, and everybody gets measured at those same occasions, that's balanced. If I have a design in which I have a mom, a dad, and a kid, fixed set of outcomes, that is not usually possible in clustered data, which are almost always unbalanced. So if you have, say, 50 states and each state has a different number of respondents, you have 30 schools and each school has a different number of students. The same number of potential outcomes is not the same. So it's unbalanced in that case. In this class, for the rest of the semester after spring break, we live balanced. So the multivariate family of models that I'm going to teach you for both regular general linear models and generalized models, as well as their path model variants, they all work for balanced data. The same set of possible outcomes per sampling unit. If you want to learn about unbalanced data, come back. Come back. So that's the world of, depending on who teaches it, it will be called, from me, multi-level models. So I offer 2 courses in multi-level models. Courses where you have repeated occasions within a person, which is longitudinal, or courses in which you have clustered designs. So I have those 2 courses is what I've done here so far. If you take these same classes over in biostat, they will be called mixed effects models. Mixed effects means fixed and random effects at the same time. If you go to another university in the education department, they may be called hierarchical linear models. Those are all the same thing. They're just different words. It's the same idea. But in those models, the options for addressing dependency have to be made group-specific or person-specific, and that requires both random intercepts and slopes. It's the slopes part that we're not going to get to. We will get to random intercepts. So just know that the stuff that I'm teaching you is a subset, but it covers a lot of ground because repeated measures designs and multivariate designs where you have certain sets of outcomes are pretty common. So let me pause there because that's a lot of words. Does this help you organize data that you're familiar with? Okay, so Hansi, what are you thinking about? What kind of data are you thinking about?
Students in schools.
Students in schools. And so what kind is that then in my taxonomy here?
Clustered.
Clustered, balanced or unbalanced?
I think unbalanced.
If you have a different number of students per school, then yeah, unbalanced. Mm-hmm.
There was also kind of a little bit of a dyadic aspect to it too, because they asked, I don't know if it's dyadic. So they have data from administrators.
Okay, administrators.
Teacher, math teacher, English teacher, and the student.
And the students. Okay, so from the perspective of administrator, math teacher, English teacher, that aspect would be balanced because like the same three conditions pop up. But if each school has more than one math teacher, more than one English teacher, more than one administrator, is that how it goes?
I think the administrator is the same. I think teacher difference.
Okay, so each administrator is tied to potentially more than one math teacher and more than one English teacher? Okay, then it's unbalanced within that kind. So yeah, I'd still call that unbalanced with potentially different outcome columns if you're interested in predicting what a math teacher thinks differently than what an English teacher thinks differently. Like that aspect could be multivariate. That would be a multivariate, multi-level model. Fun. Yeah. Okay, what do you think? Do you have data?
Crime rates over time within states.
Crime rates over time within states. So it's the same 50 states, measured how many times?
Let's say 30 years.
30 years. And so every state potentially has all 30 years. Okay, under my definition, that would be balanced. Practically speaking, though, if you modeling 30 separate outcomes at the same time is not going to happen. So we'll have to come up with ways of building in a correlation that either says basically all occasions are correlated to the same extent, or if you want to have something else, that's going to fall into the random slopes sort of thing in terms of modeling that. But you were the one who showed me an article which they called it a cross-sectional time series. Has anyone else heard this phrase?
Yes. No, I do.
I don't know what it means. Like 30 years of data is a time series, right? And you have 50 of them
Across the states.
across the states.
So I think that cross-sectional part across the states and over time parts time series.
Okay, so it's cross-sectional across the states and time series across the years.
Over time, yes.
Okay, so it's a cross-sectional and time series design because otherwise it's like they sound contradictory to me. Because cross-sectional by definition is not longitudinal, right? That'd be like having a dry rain or a hot snow, like a hot cross-sectional time series. I don't get it. But yeah, so that technically would be balanced, but in terms of actually having to model it, because there's so many, you'll have to incorporate random intercepts and slopes, which is what the unbalanced family would do. So come back to that class. Okay, who else wants to play? No one else has data they want to talk about? No? Okay, fair enough. So when, let's see here, how do you actually do this? The good news is that in some instances, we can do this using the software you already know how to use. Mixed, GLM, and their multi-level or mixed effects equivalent. So we will learn in example 4A and onward how to trick univariate software for generalized linear models to do multivariate analysis. We're going to trick it. This can work whenever you're interested in examining mean differences across your outcomes, so over conditions or over time, or you want, and/or I should say, you want to test differences in the effects of predictors. So let's say that I do an intervention and I want to make people's well-being better. That's my fuzzy word. And I have measures of things like depression, anxiety, sadness. If one of my research questions is my intervention more effective in reducing depression than it is in reducing anxiety? That's a difference in the effect of a predictor across outcomes from the same sampling unit. That requires all of the outcomes to be in the same model at the same time so that you can test the differences in those slopes correctly and directly. So in these situations in which all of the variables in the model are clearly delineated as outcomes or predictors, we can build in correlations between the observations that come from the same sampling unit directly. We can do it directly or indirectly, but it's easy to do it in the software. If you have other types of research questions that are not those, you may have to learn something new. truly multivariate software, which is, more generally speaking, software for conducting structural equation modeling. In Stata, there's an SEM and a GSEM. In SAS, there is a proc calis, although that's somewhat limited. The one that I prefer for these sorts of models is M+. That one is by far the most flexible, and that's the one that we will eventually move into for these sorts of models. But the situation in which you have to do it that way instead, in terms of your multivariate model, is if some of your variables are both predictors and outcomes simultaneously. The classic example of this is a mediation model. So in a mediation model, you would say some predictor X has an effect on this variable M, which is known as a mediator. And that mediator, in turn, is what has an effect on Y. So M, in this case, is an outcome with respect to X, but it also has to be a predictor with respect to Y. So if you have regression type relationships among your outcomes, you have to do it in multivariate software. You can't trick univariate software. The only catch that makes the first part of this different than what you might have learned in other courses is the difference in estimation. So how many of you have had repeated measures ANOVA or MANOVA, multivariate analysis of variance in courses? Is anybody? One? Okay, well then I don't have to unteach it. That's good news. So those words generally go with the use of least squares estimation. These same models we can do in likelihood estimation so that we don't have to dump people who are missing data. That's going to be the big difference. Missing predictors is trickier, but missing outcomes is going to be better addressed using likelihood instead of least squares. All right, so regardless of software, there are two main ways that we're going to change the model to build in dependency: directly or indirectly. Directly is only possible for models with normal residuals. In other words, what we're going to tell it is, hey, you know those residuals that come from the same person? Let those ones have a correlation. That's it. So it's going to have a particular pattern structure to the residuals that allows things that come from the same sampling unit to have a relationship. In that case, the linear predictor, the model for the means that has fixed effects, looks exactly the same because we're just going to allow the residuals to be correlated and call it good. But having a residual covariance, an association between the residuals from the same sampling unit, presupposes what? What do you think you have to have first in order to have a residual covariance? Yeah, say it louder, Lexi. A residual variance, right? I can't have a covariance unless I have a variance. But do I have residual variances in all models? You only have one in one. The only one that we've seen that has a residual variance is normal. The others either don't have an estimated variance at all, like Bernoulli, multinomial, Poisson, or they have a scalar multiplier that changes how the mean and the variance relate to each other, such as negative binomial, gamma, and I think that's the other two that I know. So in general linear models, if you're willing to assume normal residuals, you can put in residual correlations or covariances, but you can't in anything that doesn't have a residual variance. So what do you do instead? We have to build something into the linear predictor directly. It's an additional term that captures the dependency as a new predictor, and it's going to be called a random intercept. Then the conditional distribution is supposed to be independent across observations because the only reason for dependency was built into the model's linear predictor already. That's going to be the trickier one. That one we'll get to after spring break. Directly is what I have the chance to show you this time. So to understand the difference, we first have to adopt a new way of talking about what these models predict. In everything that I have done this semester, and usually, I use what's known as scalar notation. I don't do matrices unless I absolutely have to, because they're scary, and they're hard, and they don't really say what's in them. Am I right? Yeah. So I do things like this. It's nice and friendly. Y sub I, that's a column. Beta 0, that's an intercept. It's going to have a number attached to it. Beta 1, that's another number that's going to have a estimated. X1, that's a column. E, that's what's left over. So this works just fine if I'm predicting one outcome at a time, and all of the residuals are supposed to be unrelated. Then this is sufficient. This doesn't tell me in this notation that the residuals are independent. There's nowhere in there that it conveys that. To show that, I have to show how this model would show the prediction across all the people in the sample simultaneously. So here is the slightly scarier way of writing that same little happy model using matrices. So y sub I equals an intercept plus a slope times x plus e. I think I dropped my x. Yeah, hang on. I just saw a typo. I'm going to fix it before it goes away. There, x1. Just x. I went back and forth whether I was going to number them or not, and I think I landed on not numbering them. There we go. Here we go. Have you seen this before? Maybe? Some of you have. So this is what it looks like to write out the model in matrix form that holds everybody's data all at the same time. Y is an n by 1 number of people as rows, one column, outcome vector. Vector is what it's used if you have only one row or one column. So that'd be right here. So if I have 6 people, rather than saying y sub I write it out. Y for person 1, Y for person 2, Y through person 6. X. This is where the predictors go. So in other contexts, such as in design of experiments, this X matrix would be called the design matrix. That's more common in experimental settings where you're delineating the membership to certain groups. But more generally, X is a matrix that holds all of the fixed effects, predictors that have fixed effects. So the first column here is something we don't normally see. This column of 1s, that's for the intercept. So beta 0 doesn't have anything multiplying it because implicitly it's a 1 that goes here. We just don't usually show it. I show it in Lincom statements, and you see it in estimate statements, right? When you generate predicted values, you have to say intercept 1, and then slope and the value. That's why. It has to multiply something. So we have a column of 1s. That's what an intercept means. And then we have a column of the x variable that goes with it. Then we have the beta matrix, which holds the 2 fixed effects. And if you do the matrix multiplication, which I do not expect you to know or care about, it works out to be like this. Beta 0 times 1 plus beta 1 times x. And then last but not least is E, which holds the residuals for all 6 people. So when you express it this way, if you want to talk about how E is distributed, it looks like this. So this is the overall structure of how the E's, according to this model, are related across persons. The type of matrix that this is goes by a bunch of different names. In SAS, it's going to be called VC, which stands for variance components. Diagonal is another way to describe it. The same residual variance is on the diagonal across all the people. What that means is that this model assumes everyone shares the same common residual variance. The zeros everywhere make explicit that there are no covariances between the e's of any of these people. So this is my general linear model of one observation for each of 6 people. This is what's going on behind the scenes. Okay, with me? Now what if I change it? Well, I got to change my likelihood first. So do you remember these pictures? What am I looking at here? Yeah, or read to me, you know. Read the captions. What's this a picture of? Yeah, this is the likelihood under the normal distribution. Univariate normal, right? So if I fit an empty model, what I would get back is an estimate of the mean of this variable and its variance across observations. Those are the 2 parameters. So for any given person, I can plug in what is expected of them into this part and the residual variance into this part and find out the height. Cool. Each person has a height from this formula. Their height, if we take the natural log of it, then we can come up with the combined likelihood across the sample. Rather than multiplying the likelihoods, we can add the log likelihoods. That simplifies the math. So the log of each person's height summed across all the persons, that thing is your log likelihood. It's the combined height across all the observations, where each person's height comes from a univariate formula considering just their one outcome. That's the key. If we expand our model to include predictors, the same exact logic occurs. The only difference is that what is predicted for each person switches away from being just the one mean to being a conditional mean based on the model, such as an effective x right here. So then we have the height of each person along the regression line, where the variance around the line is supposed to be equal across people. So the mean switches, the variance stays the same. But the key idea here is that the formula for height includes only one person's outcome. And all we got to know is what their real outcome was and what their predicted outcome was, along with the model's residual variance. So rather than coming up with one height for one outcome, we're going to switch it to do more than one outcome per person. So from univariate to multivariate. So let's take the same idea of 6 observations, but what if I told you they were from 3 people and I had 2 observations each, like time 1, time 2, something like that. Most of the time in repeated measures data, people start off by structuring it like this over here on the left. So 1 row per person, where each outcome would be in a separate column. This is what's known as a wide data structure. In order to trick univariate software into fitting a multivariate model, we have to restructure it. So there's a command in Stata called reshape. You have to do it via code in SAS, but we're going from this wide to this long. What it does is change the data structure from 1 row per person to 1 row per outcome. So person 1 used to have 2 columns. Now person 1 has 2 rows. So the information about which outcome was which that used to be stored in the names of the columns has to now get explicitly represented as an index in the new structure. So T1 and T2 becomes this time column with 1 and 2. And to keep the intercept interpretable, I'm going to subtract 1 from each and change it to 0, 1, and that's going to be the x that goes in my model. So the software now, like Stata mixed, SAS mixed, still thinks I've got one outcome. I'm still going to tell it, hey model, predict y. But now all the different y's are stacked up in this same column, and we're going to differentiate which one was which by putting in that index variable as a predictor. Data management tip for those of you who work with repeated measures designs: don't use a wide structure, ever. Always store it so that the lowest level of sampling is a row, per occasion, per condition, per whatever. Those of you who work with clustered data already have data in this long structure. I can almost guarantee it. A row is a person because that's the lowest level of observation. You would have to tell it which people go with which group. So in that case, like people would be your times and groups would be your persons. So cluster data is almost always stored long by default. In multivariate data across people, it usually starts with wide. So this is the type of data structure that we're working with here. All of the outcomes are in one column. We need predictor indices to keep track of which is which. So now, same idea, starting with a scalar, trying to show it in a matrix, but now each person gets their own set of matrices. I'm introducing additional subscripting to keep track of which outcome is which. So I have YIT, Y for each individual with T for which time it is in this example. I'll swap out T for whatever makes the most sense in describing how the repeated measures are organized. Because I have two subscripts, all of my betas are going to have two subscripts. So they're going to keep track of what order I'm on with respect to either individual level predictors or time level predictors. So my general intercept is beta 0, 0 now, instead of just beta 0. My effective X, that is over persons and over times. So X was the column here that kept track of which time was which. That's a time level variable. That gets a subscript of beta 10 because it is, hang on here, damn it. I went back and forth with this and then it's wrong. It should be 01 if it's IT. Do you know why? I'll fix this and post it. Because it's the first predictor of the T part, not the I part. X varies over time. This is what happens when I make up my mind on notation 3 times. Then I have to go back and fix it everywhere I've changed my mind. E also gets an IT because E is for each time for this person. So the matrix form now describes one person's set of data, Y sub I. So there's a separate Y matrix for each person. X sub I, separate X matrix where the predictors go for each person. Beta doesn't have an I. Everybody shares the fixed effects. E gets an I. Each person has their own set of residuals. So now I have to tell it, for each person, what kind of matrix structure do I want for these two E's? I have to be able to tell it what the E variant should be at time 1, what the E variant should be at time 2, and what the covariance should be. So I got to make choices as to whether to put constraints on those things or let them all be whatever they want. Across all the people then, if you stacked up all of these individual matrices and tried to show what all the combinations would look like across the people, it takes this special little chunked pattern. So here is the model for the residuals for person 1, and then here's for person 2, and here's for person 3. So this format is known as block diagonal. So there's like pattern, pattern, pattern with zeros elsewhere. So what this is saying is that within a person, there should be a covariance between their time 1 score and their time 2 score, because they came from the same person. That covariance is estimated using everybody's data, so it's only one number. Between people, though, these zeros everywhere else, this is saying that the time 1s across people don't get to be related. The time 2s across people don't get to be related. So people are independent. Times within persons are correlated. The other thing we have to decide is whether or not we want to force the residual variance to be the same at time 1 as it is at time 2, or let them be different numbers. All of these things are empirically testable as model comparisons. So this is our new friend R. We have to decide, before we look at many of the things we care about, what kind of pattern we want in here. Now, when it's only 2 occasions, it doesn't really matter. There's only 3 unique numbers that this could be. I could have a residual variance at time 1 that's different from the residual variance at time 2, and a covariance. So do you remember these terms? Sigma, sigma squared? So sigma squared is a variance. What it is the variance of is conveyed as a subscript. So time, the first outcome, the second outcome. Sigma without a squared is a covariance. Do you remember what covariance is? It may have been a while. Remember what correlation is? Correlation is a relationship. Correlation is a standardized way of describing a relationship, right? What's the biggest a correlation can be? 1 or -1, right? So the whole reason that correlation was invented is because covariance is weird. Covariance is the difference between x and the mean of x times the difference between y and the mean of y. So the problem with covariance is that it is in the metric of the original variables. So I could tell you, I have a covariance of 10. And you'd be like, okay, is that good? I don't know. What does 10 mean? Is it like inch pounds or dog years or kilometers? I don't know what 10 is. But if I said, no, my covariance translates to a correlation of 0.8. Oh, okay, I know what that means, right? Well, these are in the original unstandardized association metrics. So we're modeling covariance because we're modeling variance. The good news is that we can compute a correlation instead of a covariance and get the software to spit that out for us so that we can talk about what the correlation is between the residuals as a number that we know what to do with. So how do we do this? Rather than using univariate height, multivariate height. Aren't these pretty? Yeah. I don't remember where I stole them from, so I can't credit this because I borrowed these a long time ago. The idea is that the formula that we're going to use for height is going to be the height of all a person's data, all at the same time. Both of their outcomes in this case. If the 2 outcomes were unrelated, you would see a shape like this. This is the 3-dimensional version of a scatter plot where all the points are just like a big circle. So this is the multivariate normal distribution of 2 outcomes at the same time. If the outcomes were negatively related, you would see this like taco looking thing, which is the 3D version of a regression line that's negative. So picture like a taco, like that's the likelihood function in 3D space. And if you had 3 outcomes, it would be 4D space, and then I can't show you pictures anymore. But the idea is that it's height for everything at the same time. And I have to show this to you, otherwise people will say my course isn't rigorous, but it looks like this. Here's the formula. So multivariate normal probability density function is the first one here. That's the formula from before. And then the multivariate normal variant of it, multivariate height, for a person's set of observations all at the same time. Switch out a few key things. F of little y, F of big Y, set of y's. Sigma squared E, that used to be residual variance of 1 outcome. Now we swap that for R, the matrix that has all the residual variances and any covariances we stick in there. Then we swap out y minus y hat. That's how we get our residuals. Well, we have more than one y and more than one predictor, so that swaps out to be x beta. So it's like y minus y hat. Sigma squared swaps out for r again. So do I expect you to memorize this? No. Do I expect you to program this? No. The idea is just What we are maximizing the height of is everybody's data, all your outcomes at the same time, building in the fact that we expect them to be related. If people are still supposed to be independent, which they are in these models, then we take the sum of these log likelihoods across people, and that's our new model log likelihood. So it's a multivariate formula for height that allows this to happen. Here's some additional stuff. There's additional complications in terms of the solution for this R matrix. This R matrix has to be what's known as positive definite, meaning that none of the variances can be zero and none of the correlations that are implied by the covariances can go out of bounds. Otherwise, SAS tries to give you answers anyway, but you shouldn't trust them. So you will start to see error messages potentially of the models you're fitting through the rest of the semester. If you see an error message that has the words in it, not positive definite, do not pass go, do not collect $200, stop, your model is broken. Not positive definite means no, something went wrong. That's what that means. Okay, how are we doing? One more piece of good news about missing data. So here's the data that are going in to this multivariate likelihood function. It's going to group the outcomes from the same person, get one height for those combined set of outcomes, get a height for the second person, and so on. The rules for what happens to missing data in multivariate analysis are exactly the same as they have been all semester. If any of your rows are incomplete, that row gets dropped. Every row has to have an outcome and all the predictors that are part of the model. Where this starts to be confusing is in thinking about what that means for a different type of data structure, this wide structure over here. I'm back on slide 10. In least squares land, where you calculate sums of squares and do all that crap, you have to have complete data to do those calculations. So if you are missing either y1 or y2, you don't have the information to get the sums of squares, they're gone. So the idea of dropping a person who is missing any of it, that is called listwise deletion. That is what happens when you try to fit multivariate models estimated using least squares. So that is why I did not teach in the introductory stats class, 6242, shout out for those of you who went through that. I did not teach you dependent samples t-tests or repeated measures ANOVA or MANOVA or any of those things, because those things need likelihood to avoid dropping cases. So least squares versions of them are quickly useless in the face of missing data. So this is good news for anybody who has some outcomes but not all of them. Your model will use whichever outcomes it has that are complete. The assumption that is being made in using incomplete information is what's known as missing at random. So there's a taxonomy related to missing data that everyone uses. There's missing completely at random, there's missing at random, and then there's missing not at random. Have you heard these words before? Missing completely at random is exactly what it sounds like. There is no reason why the information isn't there. Missing at random means there is a reason, but you know what it is. Conditionally random. More technically, missing at random means that if I were going to make one of these multidimensional likelihood mountains in multidimensional space, but I can only point to 3 at a time, that shape would be the same if I had more outcomes in there or if some of them were missing. So I've got all the information that I need to get a good height for somebody. Whatever's not there would not have changed my picture of height. That's what missing at random means. So it uses whatever information it has about the person to try and make that happen. It tries to come up with the model parameters that would result if the data were complete. If you use listwise deletion instead, that's missing completely at random, which means you're assuming that there is no reason for the missingness. Now the bad news, predictors. If you use univariate software, all rows that are missing predictors get deleted. So you've got two choices: multiple imputation or treating the predictor as an outcome. Later in the semester, I'm going to show you the latter because that is the only one I've ever done in practice. Multiple imputation is usually unnecessary if you're using likelihood. Both of these things require you to then make distributional assumptions for the predictors. That's where the trick comes in. So for now, every time that you have an example, know that you'll have to pre-select your data to have rows that are complete. That way your fit statistics and your samples stay the same across models. People don't drop in and out, of course, in different rows. So if I had 3 terms, if I had 3 observations instead of 2, no biggie. Now each person's matrix would have up to 3 rows. The R matrix for all 3 observations from the same person now has an extra row and a column. So if I had time 1, time 2, and time 3, I have a variance at time 1, time 2, and time 3. Now I've got 3 covariances. So now I have choices to make about the covariances. Do you think these should all be the same? Do you think they should get to be different? Empirical question. But it's the same pattern. And the good news is that if some people only have 2 outcomes and some people have 3, that just shrinks their individual matrices proportionately. But the overall sample is still fine. It uses, if person 1 only had 2 outcomes, their R would be a 2 by 2, and the other persons that have 3 outcomes would have a 3 by 3. It just uses whatever you got. All right, so next thing that we got to figure out, next 2 weeks from now, is what this pattern should look like. That's going to be the question. We'll use likelihood ratio test to decide that. All right, questions? Yes?
Is that also what you said is T is for the time, then it's still
Yep.
0, 1, and 2?
Yep. I'll fix this one too. Good catch. Yeah, notation is always like you have to define it, right? Because I had switched from going TI to IT at some point, and then I didn't switch the order of the things. But yeah, good catch. Good work. Yeah, I'll fix 01, 02, and make sure that I've fixed it everywhere else.
Page 11.
Page what? Page 11 too? Thank you. I'll fix that later. All right, other questions? All right, then Thursday is free homework day. Come if you want help. If I don't see you, I hope you are well. Have a good break, recharge, be healthy, and hope to see you after break. We'll see. Yeah.